LTX-2 is the new fully open-source model designed to model the joint distribution of video and audio in a single pass. Unlike previous models that treat these modalities separately, LTX-2 utilizes what the authors call an asymmetric dual-stream diffusion architecture. It packs 14 billion parameters for video and 5 billion for audio, and importantly for the community, it's released under an open-source Apache 2.0 license. To understand why LTX-2 is significant, we have to look at the silent film era of current generative AI. Most current pipelines are decoupled. You generate video first, then pass it to a separate audio model. This creates a semantic gap. Because the audio model doesn't see the generation process, you end up with footsteps out of sync, or lips moving without sound. LTX-2 moves to a joint pipeline. It processes the joint distribution of video and audio simultaneously. This captures the bidirectional dependency, where visual impact drives the sound, and phonetic cadence drives lip motion. Here is the system overview proposed in the paper. The core engine is a dual-stream diffusion transformer, DIT. On the left, the model takes raw audio via an audio VAE and raw video via a video VAE. Text is handled by a Gemma 3 encoder. These inputs feed into two distinct streams that communicate via cross-attention. The output specs are impressive. It targets native 4K resolution at 50 FPS with a 20-second context window. Perhaps most impressively, the inference is efficient enough to run locally on an RTX 4090. Let's open up the architecture. The researchers designed this as an asymmetric dual-stream system. It is asymmetric because it respects the difference in information density between modalities. The video stream is heavier, with 14B parameters to handle high-bandwidth spatial temporal dynamics using 3D rope. The audio stream is lighter, at 5B parameters, focusing on temporal dynamics with 1D rope. Crucially, there is bidirectional cross-attention at every single layer. This allows the video and audio hidden states to exchange information constantly during the generation process. How does the model ensure the sound happens exactly when the event occurs? This is what they call temporal lock. The system utilizes 1D temporal rope, rotary positional embeddings. This injects relative position info into the queries and keys, allowing the model to map visual events, like a door slam or a clap, to audio onsets with precision. You can see this in these attention maps. The model aligns visual attention for actions and phonetics directly with the audio waveform spikes. It also uses cross-modality ADA-LN, which forces both streams to denoise at the same semantic rate. For compression, the team deliberately chose decoupled VAEs. Why separate them? First, optimization. Video requires 3D compression, while audio is 1D. Their physical needs are different. Second, workflow. By keeping the latent spaces separate, this architecture enables advanced editing workflows. You can freeze the video latents to perform video-to-audio generation, or freeze audio to regenerate the video. The video VAE achieves a compression ratio of 1 to 192, which is key to enabling that massive 20-second context window. To bridge the gap between user prompts and physical generation, the model introduces thinking tokens. After the frozen Gemma 3 encoder processes the prompt, it passes data to a set of learnable thinking tokens. These tokens aggregate context and refine the prompt before it hits the diffusion model. According to the paper, this significantly improves performance on complex instructions and phonetic accuracy for speech. They also implemented modality-aware CFG, allowing independent scaling of guidance for audio and video. Performance-wise, LTX-2 is showing some very strong numbers. In terms of speed, LTX-2 is reportedly 18x faster than WAN 2.2. While WAN takes over 22 seconds per step for video only, LTX-2 handles both audio and video in just 1.22 seconds per step. In terms of scope, it outperforms models like Sora 2 and Veo 3 by offering a 20-second context window. It's also ranked within the top 3 for image-to-video quality by artificial analysis. The training strategy here followed a quantity-to-quality approach. Stage 1 was pre-training, on a massive scale using automated curation to learn diverse distributions. Stage 2 involved fine-tuning with manually curated, Foley-style data. This taught the model precise synchronization using high-quality, clear sounds. The authors claim this two-stage approach resulted in a 10x reduction in the need for expensive manual labeling while maintaining generalization. Finally, the vision behind LTX-2 is that generative media should be open, local, and scalable. It features built-in support for comfy UI and runs on consumer GPUs. The weights are available on Hugging Face, and the code is on GitHub. Regarding licensing, it is free for research and personal use, and free for commercial use for entities with under $10 million in revenue. If you're interested in joint audiovisual synthesis, this is definitely a repository to check out.